All metals exist in a regularly repeating 3D crystalline lattice structure, and in this lattice exists a sea of delocalized mobile electrons. When an electric field is applied to this lattice, the electrons will move in the opposite direction to the field. The rate at which it moves is called drift velocity. Motion of electrons is not always predictable, often moving as a result of fluctuations in temperature, causing thermal oscillatory motion, disrupting the forward motion of electrons. This results in the dissipation of energy and the scattering of electrons, which cause an increase in resistivity. Superconductivity is when a conductor expels all magnetic flux and obtains zero resistivity. Such a phenomenon occurs only when the material is cooled below its critical temperature. The critical temperature is the temperature when the electrons shift into a highly ordered state, forming Cooper pairs, and lattice vibrations no longer impede electron flow. The BCS theory states that at or below critical temperatures, when an electron passes a cation, electrostatic forces of attraction cause the cation to move towards the electron, temporarily distorting the lattice for an instant. This distortion results in a net positive charge known as a phonon, which is the vibration of the lattice. This net positive charge attracts another electron before the lattice can return to its original position. The two electrons form a Cooper pair and are the secret to all superconductivity, and as long as the pairs remain intact, the material will remain superconducting. What the BCS theory relies heavily on is a maximum temperature that superconductors can remain in the superconducting state. However, type 2 superconductors have a critical temperature which exceeds this value, yet the principle of Cooper pairs still holds true. Variations of the BCS theory have been proposed in order to explain how type 2 conductors are superconductors. The first is the resonating valence band theory. This theory states that the electron pairing mechanism is imprinted in the lead-gold structure. Neighboring lead atoms can become linked through chemical valence bonds, in which they share electrons with opposite spins. Typically, the bonding locks these spin pairs in place, preventing any current from being carried. But when the material is doped, the pairs become mobile and the valence bonds become Cooper pairs that create a superconductor. The second is spin fluctuation theory. This theory suggests that without doping, lead-gold atoms are locked into an ordered state called an antiferromagnet. That means that the outer electron on each lead atom lines up such that its spin is opposite to that of its neighbor. One electron will have its spin up, the next down, the next up, and so on. The magnetic fields produced by the spins lock the electrons in place. But in doped lead-gold conductors, the foreign atoms break up this rigid checkerboard pattern, giving the spins room to wobble. A passing electron can then set up a pulsating pattern of spins, analogous to the lattice distortions of conventional superconductivity. This disturbance then draws moving electrons together, allowing them to associate into Cooper pairs and achieve a superconducting state. A type 2 superconductor made from a lead-gold alloy and a critical temperature of 4 degrees Kelvin, SQUIDs, or superconducting quantum interference devices, are used to detect fluxons, which are quanta of magnetic flux. SQUIDs can be used to detect such minute flux through the use of the Meissner effect. The Meissner effect states that when a superconductor experiences magnetic flux, then, in an eddy current fashion, will induce a magnetic flux opposite to the applied magnetic field by the generation of persistent currents. Persistent currents are the eddy currents of superconductors, and because they form in a superconductor, they will continue to exist without losing energy. It is important to note that the Meissner effect does not occur merely with a change in flux, but occurs even with the mere presence of magnetic flux. Due to the complex nature of superconductors, they can create many different poles within the one superconductor, which is effective for detecting many different polarities of magnetic flux within a small unit of area. A key component that is so vital for SQUIDs to work is the Josephson junction, which relies on the quantum tunneling of Cooper pairs through an insulating layer between two pieces of superconductor. When a constant DC potential difference is applied to a Josephson junction, if the smallest change in current from a minute change in flux is observed, its magnitude and direction can be determined. Because the SQUID is such a sensitive instrument, it is very useful in the field of medicine to detect electrical currents and subsequent magnetic fields in organs such as brains and hearts, thus allowing them to track organ activity. SQUID's critical temperature is few degrees off zero, requiring liquid helium to cool it down, which makes it really expensive to use. However, its impact on being able to vastly radicalize the field of medicine and diagnostics vastly outweigh the cost.
And now we've reached the end of the presentation. I'd like to personally guarantee that this is the voice of one Patrick William Luke Gleason, student of Glenwood High School. Furthermore, no squids were harmed in the making of this presentation.